Meta just dropped something that the entire AI research world is still trying to fully understand. And honestly, the people who do understand it are saying this might be the closest thing we have ever seen to an AI that teaches itself how to get smarter. We're talking about HyperAgents, a system that does not just solve tasks and does not just improve at tasks, but actually rewrites the rules it uses to get better at tasks. And the crazy part is that these improvements carry over to completely different areas the system was never trained on. One test showed a score jumping from 0 all the way to 0.630 in a brand new domain, while every older system stayed stuck at 0. So let me explain why this matters and why so many researchers are saying this is the most important AI paper they have read this year. Alright, so to understand why HyperAgents is such a big deal, you need to understand the problem it is solving. For years, the dream of AI has been something called recursive self-improvement. The idea is simple. What if an AI could not just get better at a job but also get better at the process of getting it? Like a student who not only studies harder but also figures out smarter ways to study. This idea has been around since the 1990s in theory, but making it actually work in the real world has been incredibly hard. Here's the thing. Earlier system tried to do this, and the best one we had before HyperAgents was something called the Darwin Gödel Machine or DGM. The DGM was genuinely impressive. It could look at its own code, make changes, test whether those changes helped, and keep the good ones. And in coding tasks, it worked really well. The coding score on the polyglot benchmark climbed from 0.084 to 0.267 in the test set. That is a real improvement. But DGM had one big problem that nobody could crack. It only worked in coding. And the reason it only worked in coding is that coding is one of the rare areas where getting better at the task and getting better at improving yourself are basically the same skill. Write better code and you automatically get better at rewriting your own code too. But take that same system and point it at something like robotics or math grading or paper review, and the whole thing falls apart. Getting better at judging a research paper does not automatically teach you how to improve your own improvement process. That gap between task skill and self-improvement skill is exactly what DGM could not cross, and that is where Meta's team came in. The research team, which includes people from Meta's Fair Lab, Meta's Super Intelligence Lab, the University of British Columbia, the Vector Institute, New York University, and the University of Edinburgh, built something called DGM HyperAgents or DGM-H. And the key idea is almost shockingly clean once you understand it. In every system before this, there was always a wall between the task agent, which is the part that does the actual work, and the meta agent, which is the part that decides how to improve the task agent. The meta agent had its own rules, its own fixed logic, and those rules could not be touched. They were written by humans and they stayed that way. DGM-H removes that wall completely. The task agent and the meta agent are merged into a single Python program, one piece of code. And because everything is in the same place, the meta agent can also rewrite itself. The team also called metacognitive self-modification, which sounds fancy but basically means the system can change not just what it does but how it decides to get better. It is the difference between a student rewriting their notes and a student completely redesigning how they take notes, organize information, and track their own progress. Now here is where it gets interesting, because once you allow the meta agent to edit itself, something unexpected starts happening. The system starts inventing its own tools to help itself improve. Nobody told it to do this, it just happened. During the experiments, the HyperAgent built its own logging system to track which changes worked and which ones did not. It created memory tools to remember lessons from earlier ones. It built performance tracking systems to compare different versions of itself over time. It even figured out how to adjust how much it explodes based on how much computing power it had left in a given run. These are things a human engineer would normally spend weeks designing. The system invented them on its own because they made the improvement process more effective. The paper calls this emergent engineering infrastructure. It is one of the most surprising results in the whole study. Let's talk about the numbers because this is where things get wild. The team tested DGM-H across 4 very different areas: coding, paper review, robotics reward design, and math grading at the Olympiad level. In coding, using the polyglot benchmark, the system went from a pass rate of 0.140 up to 0.340 on the training data and from 0.084 to 0.267 on the test data. That matches what the original DGM could do in coding, except this time the system was not specifically set up for coding. It did this on its own. In paper review, which means predicting whether a research paper should be accepted or rejected, the system started at 0.0. It literally could not do the task at all at the start. After running DGM-H, the score climbed to 0.710, beating the previous best AI system called AI Scientist V2, which sat at 0.630. And it got there by doing something clever. Instead of just following simple rules, it built a multi-state checking system with its own checklist and decision rules. In robotics reward design, the task was to write Python code that tells a simulated 4-legged robot how to move correctly. The test was even harder than the training. The system learned on a walking forward task, but it was tested on something completely different, making the robot's body go as high as possible. The score went from 0.060 at the start up to 0.372 at the end. That is more than a 6-fold jump on a task it had never directly practiced. But the result that made the biggest noise in the research community is what happened in the transfer experiment. This is the one everyone's talking about. The team took a HyperAgent that had already improved itself on paper review and robotics tasks. Then they pointed it at a brand new domain it had never seen before: Olympiad level math grading, which means grading solutions to the hardest math competition problems in the world. They used a metric called improvement at K or imp at K, which measures how much a system can improve another agent across K modification steps. The human-tuned DGM systems, the best versions the researchers could build by hand, scored an imp at 50 of exactly 0.0 in this new domain. They could not improve at all. The transferred DGM-H HyperAgent scored 0.630. That is not a small gap. That is the difference between completely failing and genuinely succeeding. And it happened because the self-improvement skills the system built in one area turned out to work just as well in a completely different area. In fairness, this system is not cheap to run, and that matters. Earlier work showed that a single run of the original DGM on the SWE-bench coding benchmark cost around $22,000. DGM-H is a bigger and more complex system, so the compute costs are real. The code also runs with sandbox for safety because it is generating and running its own code automatically, and the researchers themselves include a warning in the GitHub repo that the code could behave in unexpected ways because of how powerful the self-modification is. The system also cannot handle images or files larger than about 5 GB right now, and it runs in fixed time windows without mid-run human input. Once you start it, it runs on its own until the session ends. There is also a deeper safety question backed into this research. The paper says clearly that as self-improving systems get more capable and harder for humans to read and understand, safety becomes much more serious. In all of the DGM-H experiments, the evaluation criteria and parent selection logic, which is the part that decides which versions survive, cannot be changed by the system itself. That is a deliberate guardrail. But the researchers are honest about the fact that the more capable these systems get, the harder it becomes to make sure the guardrails hold. It is not a crisis right now, but it is the exact question everyone in AI safety is watching. The real question now is how fast this scales. The system is already open source at the MetaFair GitHub page, which means researchers everywhere can start building on it. And the team is pointing toward future that includes self-improving robotic systems, clinical workflow optimization, and energy management. Basically, any area where the problem is complex and hard to hand-code the improvement logic for. That is a very long list. So that is where we will wrap it up. One thing that I'm thinking about now is what happens when the compute cost drops enough for smaller teams to run this. Because right now, the big labs have an edge just from being able to afford the runs, and that might not stay true for long. Drop your thoughts below, make sure you are subscribed, hit the like button, and I will see you in the next one.